Welcome to the Modern Embedded Systems Programming course. My name is MiROS, and in this second lesson on RTOS, that is Real-Time Operating System, I'll show you how to automate the context switch process. Specifically, in this lesson you will start building your own minimal RTOS that will implement the manual context switch procedure that you worked out in the previous lesson 22. As usual, let's get started by making a copy of the previous lesson 22 directory and renaming it to lesson 23. Get inside the new lesson 23 directory and double-click on the Microvision project lesson to open it. To remind you quickly what happened so far, in the last lesson you've been posed a challenge to blink both green and blue LEDs on your Launchpad board, but to do it independently. After finding out that you cannot easily do this in a single loop, you've explored the idea of running two background loops simultaneously. Specifically, you've created two such loops called main blinky1 and main blinky2, and then you tried to figure out how to switch the CPU between executing one to executing the other. This turned out to be the central idea behind a real-time operating system, RTOS, whose main job is exactly to extend the foreground-background architecture by allowing you to run multiple background loops on a single CPU, and to create an illusion of concurrent execution by frequently switching the CPU among all these loops. You also learned the new terminology, in which the background loops managed by the RTOS are called threads or tasks, and the switching from one such thread to another is called context switch. Finally, in the last lesson 22, you've worked out an algorithm to perform the context switch manually. In this lesson, you will write the actual code to automate it. Specifically, today you will start building your own minimal real-time operating system, which I abbreviated to MiROS. As I am a strong believer in learning by doing, I think that the process of building a minimal but functional RTOS kernel from scratch will offer you a deeper learning experience than trying to learn by reverse engineering an existing product, such as FreeRTOS. This is because any real-life kernel is necessarily much more complex, with features that will only make sense to you later. So it is just too easy to lose the big picture for the minutiae. So let's get started by adding a new project group called MiROS, in which you create just two files. First is the header file that will contain the Application Programming Interface, API, of your RTOS. And second is the C file that will contain the complete implementation of the RTOS. In the header file, you place the usual inclusion guards, but also, as this piece of code has a potential of being used more widely, it is a good idea to provide a comment with a brief description, copyright and licensing terms. I say here that this code is intended as a teaching aid and is not recommended for commercial applications. I decided to use the GPL open source license and include the standard language from the GPL that declines any warranties. Finally, the comment contains the contact information. The first thing you need in the header file is a way to represent your threads. For this, you can look in the main.c file, where you see that each thread requires a private stack pointer, SP, and perhaps some other information. You can capture this by providing a struct OS thread that contains the SP pointer and can be extended in the future as your RTOS grows. In the standard RTOS implementations, the data structure associated with the thread is traditionally called a thread control block, TCB. As far as the prefix OS is concerned, similar prefixes are used in many RTOSes where they serve two purposes. First is to clearly indicate which elements are parts of the operating system, OS. And the second purpose is that such prefix reduces the possibility of name collisions in larger projects, where someone might also choose the same name, thread, but for something entirely different. With the OS thread type def provided, you can now use it in main.c. you need to include MiROS.h header file and replace the stack pointers with the OS thread type. The next RTOS API you need is a function to fabricate the register context on each thread's stack. Traditionally, such RTOS service is called thread create or thread start. Here I will use the name osthread_start. The function needs to take the following parameters. A pointer to the TCB. I will call this pointer me, which is a coding convention that I will explain in a future lesson about object-oriented programming in C. A pointer to function to the thread handler, which is a bit tricky to define in C, and the best way is to provide a type def for it. For now, let's call this type osThreadHandler. And finally, the thread start function needs the memory for the private stack and the size of that stack. This signature will be augmented with additional parameters as your MiROS RTOS grows, but this is all for now. Regarding the pointer to the thread function, you need to type def it obviously before the thread start signature, as follows. It is a pointer to a function taking no arguments for now and returning void. As far as the implementation is concerned, you start your MiROS.c file with the same command as MiROS.h, and you include both stdint.h and MiROS.h header files. You copy the osThreadStart signature from MiROS.h and the body from main.c. To stitch the two pieces together, you need to establish the initial stack pointer from which to build the stack frame. As I mentioned in lesson 22, on ARM Cortex-M the stack grows from high to low memory, so you need to start from the end of the provided stack memory. As I also mentioned, the Cortex-M stack needs to be aligned at the 8-byte boundary, but obviously the user of the function might not be aware of these requirements, so it is unwise to assume that the end of the provided stack memory will be properly aligned. But you can ensure the proper alignment by rounding down the end address. One way to achieve it is to apply integer division by 8 followed by integer multiplication by 8. Next, you simply replace the SP_Blinky1 identifier with SP. You also change the main Blinky1 thread handler with the thread handler parameter of your osThreadStart function. And finally, after the stack frame is built, you save the top of the stack frame into the SP member of your osThread structure. At this point you can add some extra features, such as pre-filling the remaining stack with a known bit pattern, like dead beef here. This will make it easier for you to see the stack in memory and will help you to determine the worst-case stack use. You will see this later in the debugger view. Your osThreadStart function is ready now, so we can call it right away inside main.c. You first call it for the Blinky1 thread, and then simply replicate the code for the Blinky2 thread. As you can see, the code still builds error-free. The next feature is the actual code for the context switch algorithm. As you saw in the last lesson, the context switch must happen during the return from an interrupt, such as systick, and in principle you could code it right there. But the main drawback would be that the context switch code would need to be added to every interrupt service routine, ISR, in the system. This would not only be repetitious, but it would defeat one of the main benefits of ARM Cortex-M, which is that ISRs can be pure C functions. I hope you realized from the last lesson that the context switch cannot be coded in standard C, but rather will require some CPU-specific assembly code to build the very specific stack frames as well as to manipulate the CPU stack pointer register. However, it turns out that ARM Cortex-M offers a solution that allows you to code the context switch in only one interrupt, which will be then efficiently triggered from other interrupts or even from the thread-level code, if need be. The trick of triggering an interrupt has been already introduced back in Lesson 18, where you trigger systick by setting a bit in a special register inside the System Control Block module. Today you will use the same exact trick again, but with respect to a different exception called pendsv. Which exists for this specific purpose, and virtually all RTOSes for Cortex-M use it for context switching. I'd like you to remember, however, that pendsv is not that special, and in principle you could use any other asynchronous exception or interrupt for the purpose of context switching. To see how it will work, let's add an empty pendsv handler implementation at the end of miros.c file, build, and open the debugger. First, let's check that your OS thread start function calls fabricate the expected stack content in the memory view. And indeed, you can easily see the stack for Blinky 1 and the stack for Blinky 2. Next, set a breakpoint in your systick handler and run the program. When the breakpoint is hit, scroll your memory view to the address hex E000ED04, which is the interrupt control and state register in the system control block. As you can check in the datasheet, the pendsv exception is triggered by setting the bit number 28, which is hex 1 followed by 7 zeros. You write this value into the ICSR register to trigger pendsv. Before running the program, move the original breakpoint in systick to the next instruction and set another breakpoint in your empty pendsv handler. This setup has been already used in Lesson 18 because it allows you to determine precisely the order of preemption. When you run the program now, it turns out that the first breakpoint hit is inside pendsv. This confirms that you have successfully triggered the pendsv exception. But this is also interesting because apparently the pendsv exception has preempted the still active systick exception. Indeed, when you continue, you hit the breakpoint in systick, and only when you continue again, you end up in the main function. Unfortunately, this order of preemption is not what you want. Instead, you want the systick handler to complete, and only after it's done, you want the pendsv handler to run and switch the context. Luckily, the ARM Cortex-M core lets you control how exceptions and interrupts preempt each other by means of the adjustable interrupt priority associated with each exception. Specifically, priorities of systick and pendsv are controlled by the syspre3 register at address hex E000ED20. You can actually view this register in memory, where you can see that the systick priority is hex E0 and pendsv priority is 0. These priorities work backwards, meaning that a higher priority number means really lower priority for preemption. That's why the pendsv with priority 0 preempts systick with priority E0. If you flip it, that is, you give systick priority 0 and pendsv the lowest priority E0, you will revert the order of preemption. To prove it, let's set up the breakpoints exactly as before, and manually trigger pendsv again. When you run the code now, you can see that the first breakpoint hit is inside systick, which means that systick has not been preempted by pendsv. But pendSV still was triggered and runs just as you wanted it, and it finally returns to main. Please also note that even if you write FF into the priority byte associated with pendSV, the value reads back as E0. This is because ARM Cortex-M cores implement interrupt priority only in the highest order bits of the priority byte. Tiva-C MCU implements only 3 interrupt priority bits. Other Cortex-M MCUs might implement more bits. For example, STM32 implements 4 priority bits. So if you wrote FF to an ST chip, it would read back as F0. If you think that ARM Cortex-M interrupt priority numbering scheme is a bit complicated, you are not alone. To get it all clarified, in the notes for this video I provide a link to my ARM community blog post cutting through the confusion with ARM Cortex-M interrupt priorities. For today, however, you only need to remember that pendSV needs to have the lowest interrupt priority of all exceptions and interrupts, which you can set by writing FF into the priority byte for pendSV. This would cover all possible versions of the ARM Cortex-M cores. The pendSV priority setting needs to happen during the system initialization, so let's put it in the OS_init function. Please note that inside the RTOS implementation, I decided to use raw memory address of the syspre3 register instead of the SymSys interface, because I don't want to commit to any specific ARM Cortex-M core, such as Cortex-M0, M3, M4, or M7. The pendSV priority is at the same address in all of them, so this code will be more universal. Of course, you need to put the OS_init prototype in the MiROS.h header file, and you need to call OS_init from main. Inside the application level code, you should generally avoid interrupts with the lowest priority, because the lowest level should be reserved for pendSV. Therefore, in bsp.c, you need to raise the priority of systick from the lowest level to 0, for example. Here, you commit to a specific Tiva MCU anyway, so you can use the SymSys function nvic setPriority to set the priority of the systick exception. With the interrupt priorities in place, you now need a function to trigger pendSV. As it will become clearer later in this lesson, the triggering of a context switch will be closely related to the decision about which thread to schedule next. Therefore, the name of this function will be OS_sched. To implement this scheduling service, you first need to decide how to keep track of the current thread and the next thread to execute. This you can simply codify as 2 pointers to OS thread objects. The OS_cur pointer will point to the current thread, and OS_next will point to the next thread to run. As these pointers will be used inside interrupts, you should make them volatile. Please note that you need to place the volatile keyword after the asterisk because you want your pointer to be volatile. If you place volatile before the asterisk, you will get a non-volatile pointer pointing to volatile OS thread struct, which is not what you want. Going back to the implementation of the OS_sched function, it needs to decide how to set the OS_next pointer. But let's initially skip this step. You will see a couple of popular scheduling strategies in the upcoming lessons. For now, let's simply codify how to trigger the pendSV exception, but only when the next thread is actually different from the current thread. At this point, as with all RTOS services, you should be very careful about race conditions, which I introduced back in lesson 20. This is actually the most difficult aspect of building an RTOS in the first place. With OS_sched, you have of course plenty of opportunities for race conditions around the current and next pointers, so you need to prevent them by disabling interrupts. You have 2 options. Either disable interrupts inside the function, like this, or you can demand that the whole function must be always called from within an already established critical section. I prefer the second option because it turns out that the scheduler often needs to be called when you already have disabled interrupts, so disabling and re-enabling them again inside OS/SCHED could be problematic. With this, you can now call the scheduler at the end of your systick handler. But you need to surround it with the critical section, like this. So now, finally, you have everything in place to implement the context switch inside the PendSV handler. As I mentioned earlier, PendSV will necessarily need to be coded in assembly, but you can get a big help from the compiler by writing some code in C and then copying the compiler-generated code from the disassembly view as a convenient starting point for your actual implementation. The first thing you need in PendSV is to disable interrupts. Next, you need to save the stack content of the current thread. But you need to be careful because the first time around there will be no threads running, and the OS_cur pointer will be 0 out of reset. Therefore, you need to check for it in an if statement. Inside the if, you want to push the registers R4 through R11 onto the current stack, but you cannot code it in C, so you just leave a comment. After pushing the registers, you need to save the SP register into the private SP data member of the current thread. Again, you cannot easily access the real SP register, but you can at least fake it by introducing a local variable SP that the compiler will allocate in some register. You will then be able to replace that register with the real SP in the actual code. After saving the context of the current thread, you need to restore the context of the next thread to run. So you set the SP register to the value of the private SP from the OS_NEXT thread. As you are now changing the current thread, you set the OS_cur pointer to OS_NEXT. And finally, you pop the registers R4 through R11 from the new stack, you re-enable interrupts, and you happily return to the next thread. So let's build and test all this. First, step over BSP init and OS init and verify that the priorities of systick and PendSV are 0, the highest level, and E0, the lowest level, respectively. Next, set a breakpoint in your systick handler and run the code. When the breakpoint is hit, verify that interrupts are being disabled with the cpsidI instruction. Keep stepping through the code into OS_SCHED, and once inside OS_SCHED, update the watch1 view to see the OS_cur and OS_NEXT pointers, which are both 0 at this point. Manually set the OS_NEXT pointer to the address of Blinky1 object from main.c. This simulates scheduling the Blinky1 thread to run next. In the call stack view, verify that OS_SCHED is called from systick, which is preempting main. Step out of OS_SCHED back to systick and verify that interrupts are getting re-enabled with the cpsidI instruction. Next, set a breakpoint in your PendSV handler and run the code. The breakpoint is hit, which means that OS_SCHED has triggered PendSV. Also, verify that PendSV is now directly preempting main, so your mechanism is working. At this point, you might be concerned about the combined overhead of exiting one interrupt, systick in this case, and entering another, the PendSV exception here. After all, typically an interrupt exit involves popping the 8 registers from the stack, and an interrupt entry typically involves pushing 8 registers on the stack. But in this case of back-to-back interrupt processing, the ARM Cortex-M core skips the popping and pushing registers in the hardware optimization called tail chaining. So the overhead is comparable to a simple function call. So finally you reach PendSV with your temporary code ready for stealing from the disassembly view. You select all the machine code for PendSV, exit the debugger, and paste the code into your PendSV handler. This is the starting point for your final code in assembly. The first thing you need to change is to tell the compiler that the code inside your pandas handler function will be in assembly rather than in C. The Kyle compiler version 5 supports the __ASM extended keyword applied to a function. Obviously, this is a non-standard extension to the C language, and you would need to do this differently in other embedded C compilers. But many will actually allow you to write the whole function in assembly. Next, you delete the C code and you turn the mixed C statements from the disassembly into comments. Now let's go through the code one instruction at a time. First, let me quickly explain the disassembly. The first hex number is the address in the code memory. The next number is the actual machine instruction opcode, also in hexadecimal. This is followed by a human-readable mnemonic of the instruction, followed by its parameters. In the assembly language, you only need the mnemonic and parameters, so you need to delete the address and the opcode, as I do for the disabling interrupts instruction. The comment about pushing the registers is misaligned because the disassembler had apparently no idea that the comment represents an instruction. You skip it for now, because first you need to code the if statement, which checks the OSCur pointer against 0. Here you can see that R1 is loaded with a PC relative constant from the code memory. According to the C code, this must be the address of the OSCur variable, for which the assembly language provides a special idiom, equals variable name. You might want to remember the address of the OSCur constant, which is hex 5E8, because it will repeat a couple of times later in the code. Next, R1 is loaded again, but this time with the value of OSCur, and the CBZ branch instruction branches to the given code address if R1 is 0. You can search for the destination address of the branch, and sure enough, you find it downstream. You need to place there an assembly label. I chose the name pandas_restore because that's the place in the code where you will start restoring the context of the next thread. You copy and paste the label into the CBZ instruction. So now you have a better understanding of the code structure. Specifically, if the OSCur pointer is not 0, the CBZ instruction will not branch, so here is the place for the body of the if statement. The first thing here is to push the registers R4 through R11 onto the stack. Cortex-M actually provides an instruction for it, which is simply push R4 minus R11 in curly braces. This wasn't that difficult, was it? Next, you need to store the stack pointer into the private SP member of the OSCur structure. This is accomplished in these three instructions, except instead of the fake SP that the compiler apparently allocated in R0, you use the real SP register. Here you restore the context of the next thread. You load the address of OSNext into R1, and you load again the value of OSNext into R1. Finally, you load the value of the private SP member from OSNext structure into R0, which you replaced again with the real SP. Again, the comment about popping the registers is misaligned, so you move it to the right place. These four instructions assign OSNext to OSCur. You load the addresses and values again, and finally you store the value of OSNext at the address of OSCur. Now is the time to pop the registers R4 through R11 from the next thread's stack, which you code similarly as the push instruction earlier. The re-enabling of interrupts can be left as is, and the return from the pandas_handler function can be left as is. This is the end of the function, so let's try to build it. Oops, the code does not compile, because the assembler apparently does not recognize the OS_cur and OS_next symbols. You can fix it by providing the explicit import assembly directives, like this. Now the code compiles and links cleanly. But before running it, I still like to improve the comments and overall readability of the code. Of course, as you go over this version, you can see a lot of repetitions and opportunities for improvement. Such optimization would make a lot of sense because a context switch code like this executes quite frequently. But let's leave this to the next lesson and finish today by testing the code in the debugger. Make sure that you have a breakpoint in your systick handler and run the program. Once you hit the breakpoint, step inside the OS scheduler. Leave a breakpoint here and perform manual scheduling by setting the OS_next pointer to the address of the Blinky1 thread. Make sure that you have a breakpoint in PendSV handler assembler code and continue running. Let's step through your assembler code, one instruction at a time, to admire your creation. The first time through, the value of OS_cur in R1 is 0, so the CBZ branch is taken. Perfect. The SP register loaded from the OS_next pointer seems reasonable, so let's scroll the memory view to that SP. The stack content seems correct. Here you set OS_cur to OS_next, and as you can see in the Watch 1 view, OS_cur gets updated. Now you pop the registers, and the registers R4 through R11 look exactly as you prepared them in the OS_thread_start function. The pop instruction has obviously changed the SP, so you scroll your memory view to the new top of stack. And finally, you re-enable interrupts and you are about to return from PendSV. You step into the BXLR instruction and... whoops! Instead of returning to the Blinky1 thread, you end up in the Hardfork handler. This is not good. We have a bug. But don't panic and keep your cool. It's time for some real debugging. It seems that everything was going just fine up to the return from the PendSV handler. So let's just reset the CPU and quickly repeat the steps up to that point. So here we are again at the BXLR instruction. Now let's think how this return instruction can fail. Well, the first reason could be the incorrect value of the LR register. But it is hex FFFFFF9, which is fine. I explained this particular value back in lesson 18, Interrupts Part 3. So the next reason for a failed return can only be an incorrect value for the PC register on the stack. So let's have a look. Indeed, the value to be restored into the PC starts with hex 2. This is obviously a RAM address and not an address of any code in ROM. This is very suspect. So let's check the code that has generated this stack content, which is your OS_thread_start function. Specifically, the value for the PC is prepared in this line of code. I wonder if you can see the bug. Yes, the thread handler parameter already is a pointer to function, so taking an address of it with the ampersand operator is wrong. So this is the bug. Let's fix it. Exit the debugger. And rebuild the code. Obviously, now you need to retest the whole thing again. run the code to OSSCAD and manually schedule Blinky1 thread to run next. Continue until the BXLR return from pendSV. Check the stack content and specifically the value to be restored into the PC register. This is definitely an address in ROM, so it makes much more sense now. Okay, so let's take the plunge and execute the BXLR instruction. And what do you know? You end up inside the main Blinky1 function. So you are starting the Blinky1 thread. When you continue, you obviously hit the breakpoint inside the scheduler again. But notice that the green LED has turned on your Launchpad board. Let's remove the breakpoint from OSSCAD and let the code run free for a while. As you can see, the green LED is blinking, which means that your Blinky1 thread is now running. Restore the breakpoint in OSSCAD and manually schedule your Blinky2 thread. Run the code to the end of pendSV and quickly verify the stack content of the Blinky2 thread now. Step over the BXLR instruction and verify that you switched the context to Blinky2. When you stop inside the scheduler, notice that now the blue LED is on. Let the program run free for a while and watch the blue LED blink, which means that your Blinky2 thread is now active. Of course, you can repeat the context switch between Blinky1 and Blinky2 as many times as you like. This concludes this lesson about automating the context switch. The scheduling is still performed manually, but the next lesson will automate the scheduling as well. Specifically, you will extend the MiROS RTOS with the simplest scheduling policy called round robin. That way, you will implement a time-sharing system on your Launchpad board. If you like this channel, please subscribe to stay tuned. You can also visit statemachine.com/quickstart for the class notes and project file downloads.